Okay, so this whole next section of Unit 9 is about electrochemistry. Electrochemistry is the study of chemical reactions that produce electricity. Right, so we're going to be learning about chemical reactions that make electricity. We're going to be learning about how a battery works and different things like that. It will, on the last day, it will connect back to thermodynamic favorability in the fact of a battery is thermodynamically favored because it just automatically reacts, right? But outside of that, it is kind of like there's two parts to this unit. There's thermodynamic favorability, which is part 1, and electrochemistry, which is part 2. Now, this is not a typo. This is technically topic 4.9 that we're learning about today. It's in topic 4, and I used to teach it in topic 4, but a few years ago I realized that I would introduce, so all it was in unit 4 was introducing electrochemistry. I'd introduce it in topic 4, which is in like November, but then you don't actually use it again until unit 9. So you're like November to March. And I found I was reteaching it again anyways. And so the last 3 years I've switched, and it's been more effective this way just to learn it all at once rather than to like introduce it to you and then use it later. Okay? But anyways, that's in case you're wondering why the number doesn't match. So our idea here is a special type of reaction we're looking at known as an oxidation reduction reaction. It's abbreviated as redox. Oh man, my pencil's not working. Didn't work last period either. And I charged it all period and I thought it would. Oh, maybe that's why? The tip's like slightly twisted up? Is that a thing?
I don't know.
It's working. Okay, sorry, this just makes it easier. Okay, so redox is the abbreviation of the two together. Okay, first off, let's define these words. So oxidation, when we say a process is going through oxidation, it's the process of losing electrons. I'm going to use E- for our symbol of an electron, by the way. It's a universally accepted symbol. Okay, oxidation is the process to lose electrons. Reduction is the process of gaining electrons. Now, they always come in hand when you're looking at an overall reaction because you can't lose electrons and nothing gain it, right? They don't just get lost out into space. With this process here, it's kind of interesting because we've looked at a lot of different types of reactions this year, right? Acid-base reactions, precipitation reactions. And in those reactions, electrons were never transferred. It was just a movement of ions. There was two positive and negative things together. They rearranged to two different positive and negative things, but the original electrons never changed places. Yeah, Bryson.
Would it be E+ for reduction?
So E- is the symbol for an electron, and so it's still E-. But good clarif. I see where your brain is thinking. Lily.
What's more common to see in real life, a reaction where it's electrons are moving or a reaction where ions are moving?
I don't know. Like in real life. I don't know.
But it's not like one is like releasing and one is not.
Not that I can like think of off the top of my head, but I'd have to ponder that some more. I'll let you know. That's a really good question. I missed my face for that. So right here's our overall, everybody. Okay, now I'm going to do this as a demonstration so we can once again bring it to life. So I want you once again, when you see a chemical reaction on any problem, it's helpful even when you can't bring it to life to at least think of it in a picture form. Okay, so right here we have, what does this mean I'm reacting right there? What did I highlight in yellow? In what form, Caleb? Good. So here's my solid copper. I got some copper wire. Okay, all right. I'm going to be reacting it with this thing, which you may not know its name, but what should you know about it? It's aqueous, so how's it going to look? In water, right? So it's right here. So this right here is called silver nitrate. It's its name, right? But AQ means it's aqueous and it's been dissolved in water. So yes, it is separated into Ag plus and NO3 minus. Okay, so we're going to mix those two things together and make, so what is this going to look like when I make it? Yeah, I may not see it because it's still just aqueous. Maybe if there's a color change, I might see it, but otherwise it's still just aqueous solution. But what are we going to see? Yeah, so we should see some solid silver be made. Okay, now let's do our half reactions and then we'll do the demo. Okay, so this right here, everyone notice we just went from the overall to the net by removing the nitrate because it's not playing a role in the process. Right, it's one of our spectator ions. So the simple way to identify what's being oxidized and what's being reduced, which is the goal of today, is to track how the charge is changing because electrons influence the charge of a substance. So copper right here, everybody right, is 0 because it's a solid compound, right? A solid compound has no charge, okay? Notice on the other side of the arrow now, though, copper has become aqueous and now has a positive 2 charge. So if the charge of a substance gets more positive, is it gaining negative things or losing negative things? Losing, because electrons are negative. So this has lost 2 electrons to go from a 0 to a +2. And so that would be our oxidation step. Good. So under oxidation half reaction, we're going to write copper solid becoming copper 2 plus aqueous plus those 2 electrons that it lost. So when it loses electrons, the electrons come on the product side. And then if it was gains, then they'd be on the other side. So our silver, let's track that one. So silver started as a +1 charge because it was an aqueous ion, and then it became 0. And this maybe helps in the name of the word of why it's called reduction, is because the charge itself went down. It got reduced by gaining electrons. So then my half reaction for the reduction would be 2 Ag plus 2 electrons turns into 2 solid silver ions, or silver compounds, I should say. Notice that the number of electrons lost must equal the number of electrons gained. Right? You can't just lose them or disappear. If you go up to like the overall equation, because you have 2 1 pluses, and so each of them lost 1. And so yeah, good question though. Okay, questions on my half reactions? Okay, let's see this in action here. Okay. Now, this process is thermodynamically favored, which means what? I just put them together, at least at room temperature. I don't know if it's at all temperatures, but. Okay, so this is our silver nitrate. Looks like water, extremely poisonous water. Don't drink it. All right, and then solid, every time. Can I eat that?
Every single time you pour it.
I think you guys are always hungry or something.
Hey, I'm a curious person. Curious people go places.
Like the grave.
Maybe that's right. That sounds like.
What?
I mean, we either ask him is it a fire?
Yeah, does it explode or can I?
Is it explosive?
Those are our 2 options. Okay, here's my solid wire, everybody. I'm going to twist it up just so that it fits submerged in the beaker. But based on the fact that we know things have to collide, I'm not going to like scrunch it down because I want it all to be available to react.
Squish it.
Okay? So, yep, so it's checking that it'll be submerged. Now, it's not, it gets better as it goes. So we will see something in the beginning, but then we'll let it sit, and then in about 5 minutes, I'll walk it around again. But in the first little bit, you should start seeing some little bit of change. Okay?
Whoa, dude.
I know.
Insane.
You guys may not see anything yet, but when I come back, if you look closely, you'll start seeing a little bit of change going on with the wire.
Yeah, that's true.
Impossible. It can't be done.
Shoving it down his throat.
Jonah is tapped out.
I'm okay. You made it look too good.
Oh yeah, entropy is disorder.
Better as it goes. Okay. All right, let's try a problem where we're going to do the reverse.
Oh, okay.
Okay, so this was everybody taking an overall and changing it into what we call half reactions. Now let's look at two half reactions and write the overall. Okay, now before we do that, just for practice sake, let's identify what's being oxidized and what's being reduced. Okay, so oxidation means what? Losing electrons. So since the electrons are on the product side, in this case my aluminum is being oxidized, and that means my zinc is being reduced. Now, if it helps in remembering the definition, there's like a mnemonic device that's actually like fairly common. Like it's not, I didn't make it up, I learned it in college. But if it helps you to remember which is which, you can, the phrase is oil rig.
What?
Okay, where it just helps you keep track that oxidation is losing and reduction is gaining. So, in case you're prone to like mix it up, that can maybe help. I used to write that on the top of my test just to make sure I didn't do it backwards. Okay, now in writing the overall here, everybody, draw a line. We're going to add them together. Once again, paying close attention to the arrows. Okay, that products need to stay products, reactants need to stay reactants. And then finally, the one thing we have to check for is the number of electrons lost has to equal the number of electrons gained. So right now, as is, if I add them up, that's not going to work. So I'm going to multiply them both by something to get the same number of electrons. So the top reaction, I'd multiply by 2. And the bottom reaction, if I multiply by 3, then in both cases, it's like the least common multiple. We're going to get 6 electrons on both. Okay, so carrying that down here, we get 2 aluminums plus 3 zinc ions, turning into, now the electrons disappear in the overall. Once again, kind of because they appear on both sides of the arrow, we don't show them in the overall reaction. So then you have 2 aluminum ions and 3 solid zincs. So that would be the overall reaction for those 2 half reactions. Questions on that? Okay, I'm going to bring around our silver again because it's looking better. Now, it will keep getting better, if the number of electrons don't match. So since one was losing 3 and one was gaining 2. Yeah. Okay, Gavin, I heard a few other people say it, but I want to point out here, Gavin, what did you notice about our solution now? Right, so it's, in case you didn't notice, hopefully you can maybe see it now. It'll get better, but it's kind of turning tintage blue, right? Any ideas of what that's from? It's the copper going into the solution. So the copper wire is slowly getting smaller as the silver is getting bigger. Now, it looks right now, because it's in the shape of it, but it is not going to be in this shape. It's actually flakes of silver metal right now. So I'm going to show you, as we let it sit, the silver will grow, and then I'll stir it and it will fall off. And then that way it can keep reacting. So I'll show you, this is last classes, so it's been going for over an hour or so. So it kind of gets to a point where like it is pretty and then it kind of looks like a creature. I didn't say anything about the creature, I just said it looks like a creature. Okay, but if I look, everybody watch this, ready? So if I agitate it, then the silver comes off the wire. So can you see the wire in there? So all the silver is just clumped down in the bottom, and then if there's more silver in the solution, it will keep growing. Once we run out of silver, then it stops. But because I know I have more wire than I do silver. But technically, if you had enough silver, the wire would eventually go away completely. So we'll let yours keep going too.
Is that the designated strand?
No, actually, I had this was the one I was looking for. That's the one I used last class, but then I couldn't find it, so now I had to use this highlighter. But I'm going to clean it because I don't want to accidentally touch poisonous silver nitrate, which also stains your skin.
I was wondering if you
For a few days. But not like, I got a nice takeout. It's like I have dirt and like will wash off. So, okay, now here's the catch up today. Hopefully that didn't feel too bad. Okay? Here's the catch though. Sometimes tracking the oxidation state, meaning how in that one went from, 0 to +2, that was pretty clear. It showed you what it was. Other times it can be a little hidden and we have to figure it out. So that's what the rest of today is going to be, is learning how to assign oxidation states for every element on the table. Now, I'm going to show you a diagram that's not in your notes because I found it later, but just to kind of help prove a point here. Okay, so this right here table, you may not even be able to see very much of it, but it's a periodic table and it's showing you all the possible oxidation states for every element. The first thing I want to emphasize, an oxidation state is not the same thing as the charge that it forms. Okay, so for example, if I look at column, that's a highlighter. Right? If I look at this column, when we learned about charges, what type of charge do these elements always form in ionic bonds? Good, negative. Do you remember the number? -1. Right? Those elements always form a -1 charge because they have 7 valence electrons and they want just one more. But as oxidation states, all the dark side, so that dark of blue for chlorine, is showing all of its possible oxidation states. So chlorine can have an oxidation state anywhere from -1 to +7. So it is not the same thing as the charge. It could happen to be, because it can be -1. And some of them, they always are their charge. But that's first thing to recognize is it's not the same thing as a charge. The oxidation state is a way to track the movement of the electrons in a redox reaction. Okay? So we have a series of rules to help us identify oxidation states. Now, eventually we are going to need to have these memorized, but for this unit, I will put them on the board for the test, similar to how I put the strong acids and bases for you. But eventually we do need to know them. Okay? The other thing I want to say as we look at these rules, okay, I'm going to go through them briefly right now, and it's probably going to sound like gibberish because you don't know how it's being applied, but just stay with me, and I promise it will make more sense when we're done. B6 said after we finish this, they're like, can the whole test be this? Because that's how straightforward it was. So it might sound confusing in the beginning. I'm just saying, don't zone out on me. Stay with me. I have faith you'll get there too. Okay? Maybe you're already zoned out before I even start. Okay, now the other thing here is you'll notice with our rules, we have some that are like hard rules, like they say always. And then we have some usual rules.
What?
Right? Which is maybe like that quote from Pirates of the Caribbean, if you've seen it, of like, it's more of a guideline. than a rule, right? You know what I'm talking about? But key thing I want you to notice here with our rules, we only have rules for group 1, group 2, oxygen, hydrogen, fluorine, and chlorine. How many other elements are on the periodic table? At least 2 plus a lot, right? Like, so many don't have a rule, and so this is really going to be your main guide, is step 3 here. You use the rules for the things you have, but for all those that don't have a rule, we are going to use algebra. When I say algebra, it's simple here, okay? Simple math to solve for the missing piece based on these 2 facts, okay? Number 1, the compound of the oxidation number should always add up to 0, or if it has a charge, it should add up to the charge. So if its charge is -2, they should add up to -2, okay? If it's an element all by itself, then it's just 0 because it doesn't have a charge and it needs to add up to 0. Okay? All right, I'm going to do the first one as an example, and then I'll have you try the next ones with your table. Okay? So our goal here is we're trying to identify the oxidation state for sulfur in each of these compounds. Now, by default, to find sulfur, we're going to have to find the rest, but that's in a sense what the question is asking. Okay, so looking at A, I first look and see, okay, is there something in there that has a rule? So I put our rule list there to remind us. So hydrogen has a rule. Okay, hydrogen rule says that it's usually +1. The case where it's not is if it's with a metal, then it's going to be -1. So since it's with sulfur, the rule stands that it is a +1. So I'm going to write a +1 underneath our hydrogen there. That came from our rule list. Now, I'm going to change colors here because in order to do the algebra, we do have to keep track of total charges. But in terms of identifying the state, that's important too. So the state of hydrogen is +1. But since there's 2 of them in the compound, total is +2. So in blue, I'm writing the individual oxidation state. In red, I'm writing a total to help me figure out the other half. Okay, which means this has to add up to 0. The compound has to add up to 0, and so since this is +2 and there's only 1 sulfur, sulfur must be -2. That's your algebra. Questions on that one? Okay, part B, we have sulfur all by itself. It's not bonded with anything but itself, which means 0. So when something is all alone and doesn't have a charge, its oxidation state is just going to be 0. $11.15. Thank you. Oh yeah, so you should head to that. Oh, I don't know if you maybe take your stuff just in case. Sometimes they can be fast meetings, but okay. Oh yeah, Alex.
Is that the same for like chlorine or something with a rule? Where it's like if it's bonded to itself, is it still 0?
Yeah, good question. So even if it has a rule, oxygen by itself is still 0. The rule applies when it's like with other things. So good clarification. Okay, looking at C, so we have SCl2. So I look at the list of rules and I see chlorine here has a rule that it's usually -1. So we're going to go with it because we have nothing else to go off of. So I'm going to put -1 under chlorine. Now there's 2 of them in the compound, so that's going to be -2 total. So in order for the molecule to be 0, my sulfur in this case must be +2. So once again, notice 3 different situations. Sulfur is -2, it's 0, it's +2, right? That oxidation state can vary. Okay, coming to D, sodium has a rule because it's in group 1, so column 1. So its rule is it's +1. Oxygen has a rule, it's -2. I'm going to sum those up. So this gives me +2 total and -8 total. So then sulfur, in order to make that whole thing add up to 0, must be plus 6. Now, to clarify once again, if the question were to ask, what is the oxidation state for oxygen in this compound? Your answer is -2. Your answer is never the total. Okay, oxygen's oxidation state isn't -8, it's -2. But we needed the -8 to figure out the missing pieces. Okay? All right, last one over here, and then I'll have you try some. So oxygen has the rule of -2. There's 4 of them, so once again, -8. The difference now is it needs to add up to -2 overall. So sulfur is actually, again, plus 6. Questions on any of these before I have you try some? Yeah, Alex.
Would that be a peroxide?
No, peroxides are when,
Or is that 5? Is that 4? That is 4.
yeah, it's like the peroxide is the O isn't going to have a number, and the thing it's with will have a 2.
Okay.
Or like, I mean, I guess it could have a number, but kind of like in that one, how it's like F2O. To be honest, a lot of the oxides reveal themselves because of what it's with. If oxygen is -2, it breaks the other one's rule. So, and it's, yeah, I'll find an example to show you, but I would say once again, I'd say it's like 90% of the time oxygen is -2.
All right.
Yes, Allie.
So like, do you need your answer like be plus 6 or minus, or like -2 when you were saying like for the last one?
So since the question is asking specifically about sulfur, right, the answer is the oxidation state is +6, and then again +6.
But then if it was asking for like the O4 or something,
It would be -2.
Okay,
Yep.
that makes sense.
Because it would more likely say it'd be what is the oxidation state for oxygen. It wouldn't say O4. So, okay, you got 3 minutes. Flip the page over. Let's do practice 4.9b for 1, 2, 3, 4, 5 smiley faces. Okay. Let me know if you need any help as you work. I will warn you at the end of these 3 minutes, I will be randomly drawing a person to share their answer. So be prepared. Could be you
Oh, that.
as the chosen
How
one.
are you randomly?
I'm going to pull an element.
They got find the green ones.
Just happened to disappear.
I got 3, 4, 5, 6.
Oh wait, are we doing A?
The question at the very end.
Yes, go real quick.
Oh, he's trying to avoid the
He's like,
Oh.
we'll just save it until he comes back.
Well, we could just tell him that his name got drawn. Yes, it's a first.
Last year, that's not what I
It's, to be honest, I wouldn't.
Well, first you gotta spell the name, right? And then I just spelled his, so Melissa's here. I know his class.
I pretty much just never assumed it, but it seems like some rules are being broken with oxygen, and that's when it happens. Hydrides? for hydrogen. It just means it's with
That class is so hard. I don't know if anybody just actually.
That's the first one. Oh, no, you didn't test you. How can I help us stay new? Here, come over here. I see this scene right back. This is my least favorite scene in my life. I mean, you have to adjust. So you go off of what has a rule, and if it doesn't have a rule, it's Four is negative one, and there's three of them. And make it equal 0, and n must be. Is that what is the oxidation rate? This moment. So then, like, look on that one. There's a rule for oxygen.
Yeah.
Thanks a lot, Alex.
Okay, I feel like we're ready.
I'm ready.
You want to bring like the old songs?
Yeah.
I'm indifferent to them. I just need a timer so we can bring it back. Were you guys the one who asked to change it? Or did it just change one day? One of my classes asked to change it. But. Hey, that was quick. Welcome back. Okay, I'm going to draw a card. Everyone look on your box. The box of markers has an element on it.
Can I volunteer?
Not this. So maybe on this side. Okay, so if I draw your card, you're going to share with us what you got as the oxidation state for manganese. And then if we need to clarify why, we'll clarify why. Okay? Okay, lucky person. Sodium, which is someone at this table. Is it the one empty spot? Wow. Okay, carbon, which is my family over here. Who has carbon?
There's nobody there.
It was Garrett's. You got this one, Garrett. So tell us, what did you get from manganese for the first one? Perfect. So if you also have 3, so Garrett have 2 smiley faces for helping us out. Everyone else, you can have 1 if you got +3. Any questions you need me to walk through it? Okay. All right, next lucky person is bromine. Where's my halogen family? Very good. Have a smiley face. I guess you get 2, Zach, for helping us out. Everyone else gets 1. Not you. Okay, questions on that one? I can walk through them once again if you don't get it right. Don't be shy. Okay, next chosen person is neon, which is someone at this table. Ian, that's you. C. What did you get for manganese on C? +5. Correct. Questions on C? Okay. All right, let's hear from, I know someone's not there.
Me.
Tellurium, that's someone at the middle. Oh, Jane, looks like you. What'd you get on D?
+7.
Good job. Have a double smiley face for Jane.
Which one's the top?
Any questions on that one? And is this called a freebie? For this last one, is it so easy? Chromium, someone in our back corner. You guys are on my transition metal. Good job. Have double smiley face. Okay, questions? Do the rules make sense now? I know they sound confusing initially, but
I understand.
okay. All right, the last thing here, everybody, that we'll look at. How many should we do? One more for good measure? Okay, give me your attention up here, everybody. Eyes up front, close your mouths. So, same concept, but now it's looking at it from an overall reaction perspective. So the goal here is to identify what's being oxidized and what's being reduced. But in order to do so, we have to track those oxidation states because it's a little bit more hidden than our copper to silver reaction. Okay, so I'm going to do this one, and then I'll have you try the next one for some practice. Okay, so coming to the first molecule, C2H4, I know the rule for hydrogen is it's going to be +1. Oh, I wanted to do that in blue, though, for my pattern.
Plus or minus one.
Plus, because it's still with a non-metal. Good question, right? Which overall gives me +4. Now, notice this is different from the ones we did. There are 2 carbons in the molecule. So the individual state of each carbon is -2. Because you need to list for an individual element, not C2. Right? If a question says, what is the oxidation state for hydrogen? The answer is +1. It's not +4. Okay? All right, oxygen in the next one's by itself, so that's at 0. Okay, coming over to CO2. Oxygen is -2. Gives me -4, which means carbon must be +4 in this molecule. Say that louder, Jack. Or did you catch it? One thing I want to point out, and I think this is what Jack was hitting at, because others might be thinking the same thing. Does this 2 in front impact it? Kind of, but it's impacting both of them, so individually it doesn't change. So, but it's not bad to recognize that because that is different. And then our water here is just going to be -2 + 1. Okay? All right, now once you have your oxidation states listed, we now can track what is being oxidized and what's being reduced. So I like to kind of pair them up and say, all right, carbon on the left is -2, and on the right, it's +4. So if it increases in charge, that means it has been oxidized. Because it's lost electrons, and you get more positive when you lose electrons.
Yes.
Now, notice the hydrogen. It's not the same thing, but you can kind of have an analogy of it's like a spectator because its oxidation state didn't change. And this is where you have to look at the individual, otherwise you can get deceived. Because some people are like, oh, it went from +4 to +1. But its individual did not change. So it's neither. It's not oxidized or reduced. But our oxygen here went from 0 to -2. Now, in this case, there's actually 2 places, but it should always be changing the same. So since oxygen went down in charge, that means it has been, which that's where the word reduced comes from. If that, some people will get confused because they're like, wait, reduction is gaining, but it's because the charge goes down when you gain, and so it gets reduced. Now, underneath it or off to the side, I want you to write this really quick. It's important to recognize that if I'm identifying, like if the question says, identify the species that's been oxidized, the answer is not carbon, because carbon is not a species by itself in my reaction. You would write the C2H4, because the carbon is being oxidized in as that whole molecule. And then same thing for the reduction one, you would write O2. So keep that in mind that if you're trying to identify it, the 3 in front wouldn't matter. But yeah, good observation, Ian. Okay, questions on this? Once again, similar, a little bit different from what we just did. Yeah, Jack?
Are you ever gonna react where you have multiple, like more than 2 reactions?
Beautiful question. That was my face for that. No. So that's a great way to catch yourself is if you, number one, you have to have both. So if you find nothing's being reduced but something's being oxidized, check your numbers. Or if you find 2 things are being reduced, check your numbers. So yeah, great question, Jack. Any other questions? Okay, you got 3 minutes. Try this one, and then we'll draw 2 more cards to help us answer. Ready, set, go. This is like my favorite stage.
Oh, yeah. One Mr. Three Mr.
And you're right, because it's plus 12 total. Oh,
The summers is actually pretty good. I thought,
It's for a moment it'll be 2 years Here's our silver. I was like, what are you saying? I know, but I didn't realize like that was a shooter. Did I show you guys? Dang it! See, this is my favorite. For some reason, it doesn't look as pretty as it gets bigger.
Can I take a photo of it?
It's really cool. I should share with you guys. I have a time lapse of this growing that I made Okay, so some of you still appear to be thinking. If you need another minute, give me a 1 minute finger. Yeah? Okay, 1 more minute and then we'll check. I'll come around and show you what the silver looks like once you dry it.
You got 2 reviews?
So nothing changes in the H because over here H is oxidation.
It is interesting how like, and it kind of
Over here it stays as plus 1.
just like the weight
Well, you can't have 2 reductions. There has to be an oxidation and a reduction. So yeah, so it changes. Uses electrons as positive charge.
zero is because it didn't have
Two guys in all day.
should still only have changing zeros to their charge. There should still only be one thing being oxidized though. And one thing
Don't just like
Yeah.
My freezer size.
I don't know why you're holding it.
Yeah, you just need to
Why are you using your green
somewhere balanced.
Did I show you? Here's what it looks like when you dry Okay, here we go. I'm going to draw a card. I'd like the first person I draw to tell us what's being oxidized, and I want to know what its before and after number are. That's a weird sound. And then the second person I call him, you'll tell us what's being reduced with the before and after number. Okay? All right. Luck of the draw here goes to scandium. That's someone that you guys. You're my transition metals. Brian, is that you? Okay, so what's being oxidized, Brian? Good. So tin is going from 2 plus to 4 plus, which means it is being oxidized. Questions on that half? Okay. All right, and last person of the day, americium.
Oh my god.
That's someone at this table. Is it you, Evan? What's being reduced? And it's going from? Good. Yep. Okay, questions on identifying oxidation reduction. Yeah, Allie.
When you're writing the element out, like when you're kind of like stating this as being like reduction or like oxidized, you have to like start with this.
Yes. So like the thing that's being reduced would be Cr2O7 2 minus. Because that thing is a thing together, it's a species together. So any other questions? Almost. Okay. All right, you guys have, congratulations, you have 6 minutes to work on your homework. And it's not an option, that's what you're doing right now. You're working on your homework. 6 minutes, it's not very long. You can get a good start on it. Not 9.7, just 4.9. We were gonna maybe do 9.7 today, but I don't want to squeeze it in. So.
I missed the first day after.
Oh, do you need a homework packet?
No, I need my small reference.
Oh, yes. There you go.
Yeah, honestly, so bad. I already forget the. Well,